Well, here we go, guys. Maxima and minima problems. Thrills and spills and great, tremendously interesting questions, and a favourite area for testing students' abilities in this whole area of differential calculus, okay? So you want to be very, very good at doing these maxima and minima problems. Here's one for you. We've got a farmer has sufficient fencing to make a rectangular pen of perimeter 200 metres. What dimensions will give an enclosure of maximum area? Well, first thing you'll notice, well, actually, look, I want you to stop and I want you to do this. And then I want you to come back and resume the video when you've done it, right? Go. Okay, now you're back. The first thing that you'll notice is that there's no pronumerals defined anywhere. You need a diagram, you need some X's and some Y's and some definitions here, guys, to be able to make maths into this. It's just a worded question, isn't it? This is a major stumbling block for students all by itself. Now, there's my diagram. You'll notice that I've made the width X and the length 100 minus X, because one width plus one length would make up 100, because the other 100 comes from the other width and the other length, right? So there's my diagram. Now, I define my terms. That's what you need to do. If you're going to use X's and things like that, you need to define what you're doing so that your maths makes sense. So let the width be X meters, hence the length would be 100 minus X, and let A equal the area, capital A, and therefore I'm now going to get a formula for the area in terms of X, and then I'm going to do dA by dx, the derivative, and I'm going to set that equal to 0 and find the value of X that belongs to that situation when dA by dx is 0, and that'll get my X for the maximum area. And you reread the question, what dimensions will give an enclosure of maximum area? So you don't actually have to work out the actual maximum area, you just have to work out the dimensions. So you need the length and the width, alright? That's my game plan. See, you've got to be very careful. You've got to make sure you answer the question before you leave the question. Okay, the area would be the length times the width would be X times 100 minus X. So that is what the area is. I've just multiplied that bracket out. Okay, now we're going to do dA dx. Yeah, dA dx equals, does that make sense to you? Good. Great, isn't it? Yeah, you've got to make sure that this is all in terms of one variable. If you made this X and Y, that'd be no good. You only do derivatives with respect to one variable. So you've got to get it all in terms of the one variable. Did you know that? Well, you do need to know that, right? Now I'm going to set dA dx equal to 0, and therefore, look, it's coming out beautifully. Looks like X is going to be 50. So X is going to be 50 for the maximum area of that enclosure, right? But remember, we're asked for the dimensions, right? The length and the width. So because we know, I've explained over here the reason that it's a maximum is that because it's an upside down quadratic, right? It's a sort of a type of quadratic. We know that the stationary point will be a local max, okay? We just know that intuitively by knowing what the function is for area in terms of X. Hence, for dimensions for maximum area would be length 50, width 50, or vice versa. It doesn't matter. You don't need to label them because they're the same thing. Length 50, width 50, or width 50, length 50. They're the dimensions, and that's what you get. You don't need to work out the maximum area, so don't work it out, because if you then get it wrong, they might take a mark off you. You see? You be careful. That was a great question, wasn't it? Now, what's this one? Two variables x and y are such that x to the fourth times y equals 8. A third variable z is defined by z equals x plus y. Find the values of x and y that give z a stationary value and show that this value of z is a minimum. I can smell a gradient table coming, don't you? Well, this is a pretty interesting question because we've got z is a function of two variables where one of those variables is related to the other by a formula we're given here. Now, the whole crux of this question, guys, is that you've got to know that if you want to work out the maximum, for maximum z here, the values of x and y that give a stationary value, actually it's not max, it's minimum, sorry, but just a stationary value, you've got to express z in terms of one variable only. One variable, and there's two variables here. So you've got to fix that up so that it's only in terms of one of them. And then you can do your derivative and all the rest of it, set it equal to 0, and work out what's what, okay? That's the crux of this question. They're testing whether you know that, all right? So we've got z equals x plus y, and we've got x to the 4th times y equals 8. Now, what I need to do is get rid of basically this y out of here. Get rid of that y. It's equal to 8 over x to the 4th, and put that in that equation 1. So z is going to be x plus 8 over x to the 4th. Okay? That's the simplest way to do it. Now, that's what we do. Substitute it into 1 and we get that. Now, we do the derivative now. We're allowed to do the derivative because we've got z in terms of just a single variable, okay? Just a single variable. Now, dz dx equals, see if I've done this right, that's 1, right? And that's 8 times minus 4 is minus 32, x to the minus 5. That looks good. That looks good, and now I'm going to set that equal to 0 now. Good. And that's, I've just rearranged that equation a little bit and put the x to the 5 on the bottom with a positive exponent. Therefore, it looks to me like x to the 5 equals 32, and therefore x is going to be 2. Yes, because 2 to the 5 equals 32. Well, that's pretty good. It worked out nicely, didn't it? So we better work out, we're supposed to reread the question. What are we supposed to be doing here? Find the values of x and y to give a stationary point. Well, we've got the x value is 2. We better work out the y value now. We know that this equation here will give us the answer to what y would be when x is 2, because x and y are interrelated by that rule. Now, y is, x over 8 over x to the 4. Looks like 8 over 16, which would be a half. Oh, jolly good. So now we've got our x and our y values, which create a stationary point in z. Now we've got to show that this is actually a minimum, yes? So we need to test the gradient either side of x equals 2, and then we'll do a gradient table to show it very simply, concisely, and effectively that it is a minimum, okay? This is what you would be expected to do in an exam or a SAC, school assessed coursework task. If that's what you were asked to do, you'd be asked to show a gradient table, okay, or show some logical coherent reasoning as to why it is a minimum, okay? If you weren't using a gradient table, you'd have to show a proper argument, but if they ask you to use a gradient table, you have to do one, right? Now, alright, so therefore I'm going to test either side of x equals 2 with convenient values. I think I'll choose x as 1, x is 3, work out dz dx. Okay, that looks like that, which is minus 31. Now let's try x equals 3. Looks like I get this, which is going to be something very awkward. Who knows what 3 to the 5 is? 3 to the 4 is 81, must be 243. Good gracious, what a disgusting looking fraction. We better get that as a single fraction. Alright, but at least we know it's positive, don't we? And that one was negative, so it's playing right into our hands, guys. Okay, let's do a gradient table. Okay, what do we got? Now, this is x at 1 and 2 and 3. This is wait a minute. Abracadabra, I just fixed something up there. I had the wrong notation. It's dz dx, not dy dx. I'm such a duffer. And then, okay, what's this? The shape of z as a function of x. Yeah, let's go for it now and see what we can do with it, okay? Okay, we've got 1 and 2 and 3 there. And we've got, that was when x was 2, dz by dx equal to 0, didn't it? Right? That was minus 31. That was that horrible fraction, but it was a positive. All we need to know is, but now, did you remember me saying in a previous video you must put these values in? You must put the values of the gradients in to prove that you know what you're doing and you're not trying to fudge it. Okay, so now you put the shape in. You put the shape in this column here, and that kind of seals the whole thing in a very beautiful way, pictorially, so that nobody can argue with you. Okay, that's a negative value, that's a positive value, and then you kind of put this flat bit in here to match where that beginning, that sort of ends there. So you sort of start at this vertical position here, go flat there, over there, and then that sort of starts there like that. You can see now it's perfectly obvious that it's a local minimum, and nobody can argue with you. So therefore, when x is 2, we have a local minimum, and we've done everything we're required to do, guys. Haven't we? We certainly have. Thank you, Mr. Box. And good day to you too. Now, Mr. Box is a great old friend. Now, what's this? A cylindrical tin canister, closed at both ends. Okie dokie, like a tin can. Has a surface area of 100 square centimetres. So this is a surface area question. Don't confuse it with volume, it's surface area. Find correct to 2 decimal places the greatest volume, okay, I get it, that can have. If the radius of the canister can be at most 2 centimetres, find the greatest value it can have then. Yeah, alright, well look, I think we need a diagram, don't you? I'm a very pictorial thinker, I need pictures. So I'm going to do a diagram, whether you like it or not. See, wasn't that better? That's it. There's Mr. R, and there's Mr. H. But R and H are very closely connected cousins, because we know this constraint here. The maximum surface area is 100, so there's automatically a link, because if you increase R, guys, the chances are you'll have to reduce H to keep it all at 100 square centimetres, right? So R and H are connected. So there's a big hint in that. When you get your formula for the surface area, that'll give you the link, and you can then express R in terms of H or vice versa, so that the volume can be expressed in terms of one variable only, because we have to find what's going on for the maximum volume. Yes? We have to find the maximum volume, yeah? We have to find the maximum volume. So you have to do dVd either R or dVd H to do that. Alright, let's go. I'm rattling on too much. So, now, I hope you know the formula for the surface area. I hope you do. I hope you do, because if you don't, look, you just better go and do some measurement maths from year 10 somewhere and just get good at it. Okay, the surface area of a disc is pi r squared, so 2 of them. It's closed at both ends, it's 2 pi r squared, and this cylindrical bit surface area around the curved part of the can is the perimeter of this times the height, which is 2 pi r h, right? So that all adds up to 100. Now, what am I going to do? Therefore, see, I'm expressing h in terms of r, right? There's a reason for that. Now I'm going to fiddle around and say, well, what is my volume? My volume is pi r squared h. Did you know that? I hope you know that. Hope you know that. Pi r squared h. And I'm going to put this h there into this formula, so the whole thing is v in terms of r. Yes, there it is. It looks pretty awful, doesn't it? Oh, well, we'll just simplify it a bit. Right, cancel that. Cancel one of those r's. You get this. Oh, that wasn't so bad, was it? Not at all. Now we can do dVdr and set it equal to 0. Work out r for v max. They don't ask us to prove it, do they? Oh, goody. Well, we can just... it'll be pretty obvious anyway, because it's a negative cubic. Once we get the graph happening, we'll probably we should do a graph. Upside down cubic, so it's going to go zoom, and part of that graph will be the bit that we're interested in, because obviously r can't be less than 0, and certainly can't be more than a certain value, because the volume is going to go negative then as well. Stop your rattling on, Wolfman, and do the work. So therefore, dVdr is this. Now we're going to set that equal to 0, and therefore, what is r? What is r? Well, it's going to be easy. Just solve that for r. There you go. So it's going to be the square root, the positive square root of that. Excuse me. Because r can't be negative. Okay, the positive square root, because r can't be negative. Looks like it works out to be 2.30. That's very interesting, because see, this part of the question here says we're only allowed to go up to 2. So that's going to be a classic absolute max and minimum kind of scenario, and I covered that in a previous video, absolute maxima and minima. Okay, so where are we, guys? We've got R, we got you, Mr. R. Now, what are we supposed to work out? Find the greatest volume. Okay, that's alright. Well, we'll just plug that into the formula for the volume, which is this one here. 50R minus pi r cubed, right? There it goes, and what do we get? Okay, 2 decimal places, is that what we need? Yes. 76.78 cubic somethings, and they're centimetres, aren't they? Yeah, centimetres. Good, we've done it. We've done it. Yes? Now, the second part of the question is if the radius of the canister can only go up to 2. Yeah, okay, I get that. We better do a little graphy, I think, somewhere here, just to get a feel for what's going on. We've got an upside down cubic, as I was saying on the previous screen. I'm factorising it to make it even clearer what's going on. Yes, and we're saying if v equals 0, I'm getting the intercepts, right? The r intercepts, if you like. Therefore, r would be 0, or r would be that thing, right? Just that's from the null factor law. If I set that equal to 0, you get this, don't you? You do. Now let's do Mr. Graph. Hello, Mr. Graph. Yes, I am insane. I talk to graphs and boxes and everything else, but I'm happy, so, you know. There, see this. If you actually solve that, you'd get r would be plus or minus the square root of 50 over pi. So I'm just showing you what the actual graph, all of the graph would look like. But obviously we're only interested in the bit where r starts from 0 and goes up to here, right? That one there, and that's positive square root of 50 over pi. Okay? Do you get that? Now see, obviously this is the bit. This is the bit of the graph that we want, right? We don't want this end point here, and we don't want this end point there, because we don't want 0 volume. It just seems to be pretty pointless, doesn't it? So this is the bit we're dealing with, guys. This is the bit we're dealing with. Okay? Now, this is the Vmax was when we had 2.3, wasn't it? And we can see quite clearly from this little diagram here, which is just so beautifully illustrative for our purposes, that if we're allowed to go r anything up to 2, then we'd be to the left of the point here at 2.3, where r is 2.3, where v max is. So therefore the maximum value that we're going to get is when r is actually at 2, right? If, on the other hand, the value of r that we were allowed to go up to was to the right of 2.3, okay, anything from 0, not including 0, up to, say, 2.5, for example, then you would know that Vmax would be anywhere from here up to there, which would actually include the actual local max point there. So it would be that Vmax for that scenario, say 2.5, if r was allowed to go up to 2.5, would be the actual Vmax. You get me? It just depends on where you are in relation to where the maximum is of this curve. Have I explained that well enough? I hope so. So as can be seen from the graph, we know that r is allowed to go from 0 to 2, and therefore Vmax for our purposes, V absolute max for our purposes, with a domain of 0 and not including 0 up to and including 2, would be the actual value of V at 2. And we can find it out by plugging it into the formula. And there she goes. There it is. Did they want 2 decimal places? I think they did. I think that's it, guys. Did you get that? Do you understand? Jolly good show if you do. Now, why don't you pause the video and have a go at this one now? This one's actually quite a gritty one, okay? Trying to come up with a formula in the first place is a little bit hard. So pause the video and come back when you're ready. Okay, how did you go? How did you go? Did you find it hard? What did you find hard? I tell you what I found hard was originally getting a formula going for one of these equations that I needed. Now, what do we got? We've got a TV cable company, and it's got 1,000 subscribers who are paying $5 a month, okay? I think I could go for that TV cable company, not like the prices they charge here. It could get 100... it can get 100 more subscribers for each 10-cent decrease in the monthly fee. Okay, what rate will yield maximum revenue? So, right, so we've got to look, we'll have to define some variables here. This is a worded question which is the bane of many students' lives, okay? So I need to get some pronumeral to represent revenue. I probably need another one to represent how many subscribers I've got, I'd say, because the whole thing depends on how many subscribers the revenue depends on the number of subscribers and the monthly fee, doesn't it? Let's see if we can put that in words that we can understand, symbols that we can use. So I've let R equal the revenue, and I've said N could be the number of subscribers. They seem to me to be the most obvious pronumerals to use, right? And you always look at what they ask for to get a hint as to where you start with defining variables. See? What rate, okay? So, well, I think what I've got here is good to go. We'll see where it leads us, and we'll see if we need to revise what I've done. Now, M is the monthly fee. M is the monthly fee, so that's really what they're asking us for. You need to define that, right? I've got so many variables here, they're coming out of my ears. I hope I need them all. Let's just see where we go with it, as I said. Now, the first equation is that the R is the revenue, that's the money that comes in, is equal to the number of subscribers times the monthly fee. All right? Now, secondly, we need to get something which basically ties up mathematically all this palaver up here about how many subscribers you get, right? You've got 1,000 to start off with, haven't you? I think so. 1,000 subscribers, yes. Now, what it says, let's read it again carefully. You get 100 more subscribers every time you drop 10 cents off the monthly fee. Now, you've got to try and put that into a formula for N, the number of subscribers, okay? Now, sometimes it helps you, if you have trouble with that, just doing some practical examples with actual real numbers to get a feel for it. So let's think about that. If you had 1,000 subscribers, okay, that's how many you got with $5 a month. Now, you think about it. If I went $4.90 a month, how would you work out how many subscribers you get? You've got to think about that. Well, you'd work out, well, how much is the drop? The drop is 10 cents. So how did you get the 10 cents? Well, you subtracted $4.90 from $5, okay? And then you would basically times that 10 cent drop by 100, and you would add it on to the initial 1,000, right? What about if it was $4.10 a month, right? Well, what I would do, now I'm starting to get a feel for this, I'd subtract $4.10 from $5, and I'd say, right, that's 90 cents. How many lots of 10 cents are in that 90 cents? Well, if you divide 90 by 10, take note of that. You divide the 90 by, or the $0.9 by $0.1, you'll get 9 lots of 10 cents. And you multiply that by 100. Now, are you getting a feel for it? Because here it comes. You ready? Good heavens. Well, it's just what we did. Look, the number of subscribers is $5 minus whatever you're charging. In the example we were just doing, we said $4.10, I think. Okay, so take that off the $5, work out how many lots of 10 cents are in it, and times that by 100, and add that to your original subscription at the $5, the number of subscribers at the $5 fee. That's how you do it, isn't it? You think about it. It works fine. It works fine. But doing practical examples, if you have trouble getting formulas out of all this gobbledygookly words, this is the best way to do it that I know of, okay? Now, where was I? Meanwhile, back at the ranch. We've got to get a formula for revenue, right? Revenue. So, it looks like it's N times M, where N is this beastie. Oh, that's great, because we'll get the whole thing in terms of M. Then we can do dRdm, can't we? Yes, of course. M has to be less than or equal to 5. And it certainly can't be negative, of course. That's pretty stupid. You'd be giving people money away if it was negative, all right? So can you just implicitly assume that I'm saying from naught, greater than naught, and up to and less than 5, yeah? All right. I'm exhausted already. Now it's the easy bit now. We've got the formulas in place, so substitute for N from 2 to 1, and we get that. All right, well, that's doable, guys. That's doable. If we multiply out the brackets, we're going to get that, and then we're going to get, oh, that's nice, isn't it? And then we're going to get that. So look, we've got an upside down quadratic. So therefore, this is very interesting. We're going to get a local max. All we need to do is do dr dm, set it equal to 0, find out what m is, and that is the rate, which will yield the maximum revenue. And then we've got to plug that basically into the formula for the revenue, which is now this beautiful formula, and we'll get R max. See? Easy as. Yes, that deserves a box as well. So that's our formula for revenue. We're delighted to see you, Mr. Formula for Revenue. DRDM is that easy. See, this is the easy bit now. We've done all the hard yards. Set it equal to 0. We get that, and therefore we can say that M would be 3. Oh, good heavens above, $3 a month. Isn't that interesting? It's very, very, very interesting. And thank you, Mr. Box. Now, we better plug that. We're supposed to get the actual maximum revenue, aren't we? So we plug M is 3 into our formula for revenue, which was this one with the box around it. And yes, I've explained, because it's a quadratic, it's an inverted quadratic, we're going to get a max. So, you know, we don't have to verify anything about local maxes and mins. We know it is a local max. So R max is that formula in the red box with 3 substituted into it, and it's going to be very exciting. Roll the drums. 9,000 smackaroonies. Okay, that's very interesting, isn't it? That's the revenue per month, yes? And it's very interesting because when we had 1,000 at $5 a month, they were only making $5,000, yeah? So this is a very, very fascinating way of doing maths to analyse a real-life situation, which I could imagine would be a real-life kind of situation, yeah? Alright, so $3 a month subscription rate gets a $9,000 a month monthly revenue, which is a max. And you're a star. So you better go ahead now, armed with the confidence that you've gained from looking at all this, go ahead and do heaps of these questions, because they are the types of questions that they examine you on. Okay? See you later.